Good afternoon, everyone. I hope you had a good lunch. So I guess after lunch, I want to start with a little bit of exercise and a bit of show hands. So I want to ask if anybody or... Oh, okay, sorry. So how many of you have heard about Julia? Wow, that's a lot. Oh no, I did not expect that. Okay, how many of you don't know about multiple dispatch? Okay, and how about just-in-time compilation? Okay. Well, that's good. I hope everybody can learn something new today. So I want to start with a disclaimer that I'm not designing or developing the Julia language. I am a programming languages researcher. Currently, I work as a postdoc at Purdue University. A lot of my research happened to be on Julia, and I have come to appreciate this language quite a bit. So today I want to share a few unusual design decisions that the Julia language made. And as John pointed out at the opening of this LambdaConf, it's not uncommon for programming languages to coin some idea or language feature or even implementation trick, and for these ideas to trickle and spread to other languages. So that's why today I want to share a few things that I think might be interesting for a broader audience of language designers and software developers that we can learn from the Julia language. So I call this talk Practical Restrictions, and I've dubbed those design decisions as restrictions, but I don't expect everyone to necessarily agree with me that they are either practical or in fact restrictions. Somebody can think of them as superpowers, but I hope you will see what I mean by the end of the talk. So let's start with a short intro to Julia. So it's a fairly new language. It's been around just over a decade by now. It was designed specifically for scientific computing. So the design goal was to make a new programming language which would be both easy to use for non-professional programmers and also very efficient. And it's hard to imagine that both of those goals can be achieved, but we'll talk about how Julia can, in fact, do that. So for performance, Julia relies on a just-in-time compilation. For easy to use and productivity, it might look a lot like languages like Python or R or MATLAB for people familiar with scientific computing. But what's very unusual about Julia is that the whole design is built entirely around multiple dynamic dispatch. So the idea of multiple dynamic dispatch, and we'll come back to it in a second, it's not new. It has been around in languages starting from Common Lisp many decades ago. But Julia took it to the extreme, and every single function call in Julia is a multiple dynamic dispatch call. And so to make this work in the context of scientific computing and make this efficient, Julia had to make certain sacrifices, and that's what I want to talk about. So to start off, Julia, like in functional languages in Julia, data type definitions are completely separate from function definitions. Like in object-oriented languages, we can define data types like big integer here, which are subtypes of some other nominal types. So like in object-oriented languages, we can have this nominal subtyping hierarchies. And then when we define a function, we can provide a type annotation on a function argument. But what's interesting, we can have multiple different method definitions for the same function. Moreover, those function definitions don't have to have the same number of arguments. So this may look a lot like static overloading, if you're familiar with languages like C++, for example. However, what's important distinction is that in Julia, the process of choosing the best definition of a specific function happens at runtime dynamically, hence multiple dynamic dispatch. So we have multiple arguments, they can have different types, and at runtime, using specific types of values at runtime, we are choosing the most specific applicable method for this particular function call, and that happens dynamically. And again, every single function call is resolved this way, and there are hundreds, sometimes several hundreds of methods for one function in Julia standard library. it's really hard to imagine how can this be made efficient, and why would you go this route of making everything dynamically dispatch? However, remember, we're in the context of scientific computing, and there it's very important to allow for code reuse and extensibility, or composability in a way. So just as a sort of high-level example, imagine we have some complicated computation, which is called hard problem here, and it works over arbitrary collection of elements. And it doesn't matter what representation those elements are, we're just interested in having some collection. The only thing we need is the fact that there is a plus for those collections inside this hard problem. However, maybe in our specific domain, we know that we are dealing with only collections where all the values are the same. So we can provide a very efficient representation of such a vector where we just keep this one single value and the number of elements. And then, of course, we want to reuse this existing complex computation for our very efficient little representation for our new data type. So we want to compose an existing library or an existing algorithm with a new efficient representation. And the only thing we need to provide for this to work is to provide those little building blocks that the generic implementation relies on, in this case, plus. So as long as we are defining plus for our new data structure, we can simply reuse a complicated existing algorithm. So thus we have this way of reusing existing code, but we're also providing efficient implementation for our domain. And that's great for the context of scientific computing. However, at this point, you might be wondering, like, why are we calling Julia a dynamic language? Like, we have all those type annotations everywhere, right? We don't have to. It's completely optional. Like, for example, we can define this twice function. We don't provide any type annotations. And we can call it with any value. And as long as all those building blocks, like plus, are defined for a specific type that we are calling twice with, everything will work, and we will use the plus definition, but if there is no such method as in the string case, we'll get a runtime error. So there is no static checking, we can get those errors, and we don't have to provide type annotations, but if we want to provide a more specific implementation, maybe a more efficient one, or just some different behavior, then you can provide a type annotation for your desired data type definition, and you'll get a new behavior. So now, finally, how can we get efficiency here? Well, the key in Julia is that every time we call a function with a new set of argument types, Julia compiles this method for this specific set of argument types. And because at runtime we know concrete values and we essentially know everything about the representation and the dispatch behavior, we can generate a very efficient representation, which is essentially like a statically typed piece of C code for a specific runtime function call. So the Julia implementation, every time we call this one of those methods, it will generate a specific optimized version of the twice function. And in particular, it can eliminate dispatch, it can inline the definition, and simply go and call a primitive integer addition for signed integers. And I will not talk about how exactly Julia does that. The next talk in this section, the unreasonable performance of Julia, will focus exactly on that, how this JIT compilation works. I just want to tell you at a high level why it works. And this brings me to this first practical restriction I'm talking about. So remember I said Julia, like in object-oriented languages, we have subtyping, but it's just subtyping. There is no inheritance, meaning we cannot reuse data representation when we are trying to make a subtype definition. So whenever there is a data type definition like the struct we saw in the example earlier, or a primitive type like integer, this is called a concrete type, meaning we can create a value of this type or with this type tag, but we can never create a subtype of such a type. So unlike in case of classes where we can make like a subclass to reuse some data type definition in the superclass, we cannot do that. The only thing we can do is to reuse the algorithmic part by using multiple dispatch and subtyping. So we can have those abstract types, which are completely sort of empty. They don't contain any data, but they do form those subtyping hierarchies, and they enable us to have these generic implementations which don't care about particular definitions. So we have composability and generality using abstract types, but as soon as you want efficiency, you have to think about the concrete data representation. And the reason Julia can optimize this code for concrete types so well is that there is no unknown there. You know everything. You know the data layout. You know how multiple dispatch would be resolved for such a type. So essentially, it's a little piece of statically typed code once you get to this concrete type arguments. So it seems unusual to have subtyping but not have inheritance. However, we still get this benefit of having multiple dynamic dispatch, which is great for this context of scientific computing, right? We have composability, we have everything. But by giving up a little bit of data reuse, we are able to gain a huge power to generate optimized code. And that's why I think this is a practical restriction in this case. Okay, one more quick show of hands. How many of you are familiar with the eval, generating code at runtime? Yeah, okay, quite a few. So just in case you're not familiar, like in dynamic languages like JavaScript or like R, there is such a function, it's called eval, where you can essentially pass a piece of code and it will parse and maybe compile and execute this piece of code at runtime. So we don't know the code in advance. It can be even generated at runtime, but we can evaluate such a code. And the interesting question is what happens when we are trying to not just maybe evaluate some expressions that we are reading from a read line, but to actually generate new piece of code, like generate a new function. So here is a simple example where we have a sum3 function. It just takes 3 arguments. We add the first 2. Then we run eval, and we are trying to redefine plus to return just the first argument. And then we call the plus again. So if we are in traditional dynamic languages, here is a question for you. What would be the result of this function? Or just based on your intuition, how would the eval work? Yeah? 3. Interesting. Okay, any other guesses? 6. Okay, cool. So what happens in traditional semantics, right? We run plus. So the first time we run it, we get 3. Right, then we run this eval function. It redefines plus, and we immediately call to this plus again. So it returns the first argument. Oops, and we get the 3 as a result. However, I am so grateful we have this member of the audience who thinks that 6 would also be a reasonable answer, because that's not what happens in Julia. Right, in Julia, it looks like when we are running this sum3 function the first time, it looks like nothing happened. Like eval didn't even work, so we just use regular plus, which does addition, and we get 6 as a result. But once this first top-level call is finished, then we sort of see this new definition that eval produced, and then the next time we call sum3, we are just using the new definition both times. So both calls to plus inside sum3 resolve to the same exact definition of plus. So in this case, we are getting 1. Okay, so let me briefly talk about how this works, and then we discuss why does it make sense. So in Julia, because we have multiple dispatch, we can have many definitions of functions with information about the type arguments and so on. But we also have this world age counter, which essentially just counts it's a global counter that counts how many total method definitions are there at the moment. And every time a new method definition is defined, we just record this world age counter as a birth age. So then imagine we have some method table with some existing functions. We have currently world age at 10, and then we define this sum3 in a REPL. So we increase the world age counter to 11. We record this new definition of sum3. And then when we are making the first top-level call, what happens is that all the function calls inside the currently running top-level call, they only see the world age at the moment of the call. So they can only see this subset. For some reason, it's not showing some highlighting. That's a bit confusing. But when we are making those calls inside the top-level call, we only see the subset of the method table at the moment when the top-level call happened. So when this eval function runs, we add a new definition of plus with a larger world age, but we can only see the subset up until 11. So whenever we are resolving this plus calls, we just see this single definition of plus, so both calls resolve to the same one. That's why we get regular 6 as a result. And then when we'll be running sum3 the second time, because we'll be starting at the world age 12, we will see the new definition of plus, and both calls will be resolved to the same one. So sometimes, like if you really need to see this new definition, it's possible to do that in Julia. However, like there is a special function which allows you to call this very new definition. However, it's much slower. And the reason is that Julia's JIT compiler, so the decision they made is that whenever we make this top-level function call, right, we can run optimizations, we can generate type-specialized version, optimize, get this cool performance. But because we don't know what eval will generate, and we have this nice semantics, but because we don't know what eval will generate, sort of we are deciding to have this nicer semantics which limits sort of the state of the world that we see at the point of compilation, so that we can resolve multiple dispatch, we can run all the optimizations, and we don't care what happens afterwards, even if eval works. So the JIT compiler doesn't have to bother with like trying to check, is there a new definition, is my optimization correct or not? I just compile as if I'm running some function without any eval whatsoever, and we can get a lot of performance, again, much like in statically typed programming languages. However, sometimes you might need this feature. But based on our research, it's not that common. So it's a very conservative estimate that sometimes packages and programs do have to use eval. However, the main way people use eval in Julia for code generation is to generate boilerplate code. So imagine maybe you have some library and you want to define Julia wrapper on that library, and you're just running through a bunch of fun method names and calling a mapping main from the underlying library. So instead of manually defining those functions in the source code, you can use eval and for loop and just generate this automatically. So it's like metaprogramming, and usually it happens at sort of you have this explicit phase of code generation. So you use eval, you generate all this code, and then when you're done, you can get all the performance you can get from Julia, and you don't care about the world age semantics. So in most of the cases, you wouldn't even notice that something is different in the Julia semantics of eval compared to other languages, because there is just no way of exhibiting this difference. Okay, so this is another example where to gain performance, we have to restrict somewhat expressivity. Like it's not entirely restricted, right? You can still get regular eval semantics if you really need it, but in that case, you will know that, well, I won't get as much performance as I normally do. And another huge benefit of Julia's approach to JIT compilation, both because it just does this type-based specialization and this world age semantics, is that it's very predictable, which is very important in the world of scientific computing. So the first time you're making a function call, Julia compiler will do a lot of compilation. It may take a long time, and of course, people might be unhappy about it. But if you're working with a huge data set and your computations run days, you can run this once, get the efficient compiled code, and then you know that no more JIT compilation will be happening during your computation. You won't get some unusual behaviors like you normally do with JIT compilation, like in Java, where sometimes JIT compiler decides to de-optimize something, then optimize again. So it's very opaque. In the case of Julia, users know exactly when JIT compilation happens, and they pay the price of compilation upfront, and then they just get very efficient code, and they can use it for their expressive computation. So this brings me almost to the end of the talk. I just want to sum up the talk and say again that Julia had a very ambitious goal of reconciling the ease of use of a language with high performance. So it wants to be both easy and fast. And they dare say it's not possible to do that without making certain sacrifices. However, I think that Julia designers found a really neat ideas where we can give up just a little bit to get a lot of benefit and performance in return. So maybe next time you have a set of constraints or goals that seem impossible to reconcile, maybe there is some little restriction that you can make to make this all fit together. And I think that's a very interesting idea to take away from the Julia design. Thank you very much, and I'll be happy to take questions.
Thank you for your talk. Something that's always fascinated me about the Julia approach is that it seems like a clash of cultures, right? How much would you say these sorts of details are features for the scientific community rather than bugs? Like, if you're a scientist, you don't really care about some of this stuff, you just want it to behave a certain way. Are they attracted to this kind of stuff, or are they kind of put off by the nerdy computer science stuff, but they just like the frameworks and stuff that use it?
So I think what happens is in most, there are sort of two ways. One is when people are trying to just take some existing code, like their code in Python, it can be easy to write it to rewrite it in Julia in a way that would be prohibiting performance and like just prevent optimizations. So in that case, people come to Julia forums and they're upset because it's not working as fast as it's promised. But usually there is a way to write it sort of in a conventional Julia style to get a lot more performance out of it. And sometimes you need to understand those details about how JIT compilation works and why you need to write your code in a certain way. And I think the next talk will also highlight this, like some of the specific properties of the code that need to be met to get most of the performance. However, there are also a lot of people who maybe they're just starting their like programming for their field, and they're just writing, like if they're starting with a Julia tutorial and they follow some tips, they don't usually need to understand all those details. So in many cases, like in that twice example, you just get very good performance or without thinking about it hard. So I think it's when you are getting some performance bottleneck, in that case it might be that you need to go and read more about Julia's performance and how the JIT compilation works. So like, as usual, it depends, it really depends. Sure.
Are you familiar with modular and Mojo?
Modular?
Modular and the programming language Mojo from Christian Lattner?
Not sort of as a, like I heard of it, but
I'm just curious if it's going to end up going after the same audience, but using the compiler for the optimization as opposed to the JIT at the runtime. I was just curious if you had any thoughts on that. So.
No, unfortunately not.
So there was a funny couple of numbers in the world age. The evaluation, it was saying that like 4 to 9, yeah, this one, 4 to 9% of Julia packages bypassing. So first 9, for example, doesn't sound like it's low. Like it's like almost like every 10 packages, it's not too little. And like, why is this wide variation? Why is it like?
Yeah, it's a very conservative estimate because we were running first a static analysis trying to find statically those calls to like invoke latest. Another way of calling bypassing world age is by using eval itself. And the static analysis, because we are parsing code, sometimes it's like most likely what we are parsing is not actually a like bypassing world age, but we are just for the sake of like having this analysis efficient, we're just sort of for everything that's not, we don't know exactly what it is statically, we are assuming it might be bypassing world age. And then we, for like a subset of this, we went and did a like manual check and saw that, yeah, a lot of those things are not actually bypassing world age, and also ran some dynamic analysis on a subset of packages where you also see that like mostly none of those things bypass world age. But because we didn't do the whole dynamic analysis for every single one of those, it's like this range of, yeah, and it may be that it's just like one function that has an eval in the entire package, but it's not affecting much of the code. Well, I hope you'll check out Julia if you haven't. Thank you.